the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
The Stevens Institute of Technology is proud to present the Hugo New Corporation Sustainability Seminar Series, co-sponsored by Geocentric Consultants, H2M Architect Engineers, Brown & Caldwell, and BEM Systems.
Thank you so much. Thanks, Samir. Thanks for having me here, and thanks for being here this last seminar of Sustainability Seminar Series. I'm very happy to be here, and I'm thankful that Samir and Dr. Sarkar invited me to come here and share some of my research with you, given especially the fact that, as you've heard, my background as far back as you go is all civil engineering, has always been civil engineering. Don't ask me why I'm not with civil engineering now. That takes an hour by itself to explain. But I'm always happy to share my research and experiences with specifically civil engineering students. So I'm assuming a lot of you are housed within the department. I have been with Stevens since 2015, but as a faculty, and as it was said, my background as far back as you would go, I'm hard to admit, over 20 years been in the transportation industry. So I've been working in the states of California, Nevada, Pennsylvania as a transportation engineer, transportation consultant for many years, bless you, before deciding to go and pursue my PhD. And over the last decade specifically, the focus of my research has been under two umbrellas of sustainability and driverless vehicles, either both together or separately, but those are sort of like the two domains that I've been mainly focused on, or my research has been focused on. Today I'm bringing both of them together to present a research piece to you guys under the title of Automated Vehicles, Energy and Environmental Cost Savings. So we're going to be talking about the impacts of automated vehicles, or what you guys probably know as driverless vehicles, self-driving vehicles. There are different terminologies out there for the technology and how they could potentially impact our energy sector, environmental issues, and so on. So let me start by showing you this famous figure from EPA that gets updated pretty much every couple years, if not every year, that shows how much each of these industries contribute to greenhouse gas emissions. When you look carefully into this slide, I've been told that I cannot move much, and this is the hardest thing for me. So is this okay? Okay. So you'll see that transportation sector is contributing 29% of greenhouse gas emissions, higher than just about any other sector that you see here. This has changed, unfortunately, over the last couple of years. The electricity sector, which is basically the blue band that you see here, used to be the largest contributor to greenhouse gas emissions, but as of a couple of years ago, transportation sector got the badge of honor unfortunately. And now we are, those who are in the transportation sector, or those of us who are contributing in any shape or form to the greenhouse gas emissions, we kind of like have the largest contribution to greenhouse gas emission. This change over the last couple of years is not because we have done anything differently within the transportation sector. It's because the electricity sector have been doing better. So they have actually decreased their contribution to greenhouse gas emissions, and as a result of that, transportation sector became number one contributing, or the largest contributing sector to greenhouse gas emissions. And you would be interested to know that 60% of that 29% of transportation sector's contribution is coming from what you and I drive. Usually people think that the largest contributing factor of the transportation sector is airplanes and in the airline industry. That is not true. It is basically the cars, SUVs, minivans, motorcycles, anything that we drive does have the largest contribution to greenhouse gas emissions. Trucks, not the tractor trail trucks, because we have a different category for medium and heavy vehicles, and they are the second one at 23%, and then it goes to aircrafts, rail, ships, boats, and others. But again, 60% from what we drive. And this is not it. CO2 emissions from transportation sector is not the only concerning point of this. Of course, we're concerned for CO2 because of greenhouse gas emissions and climate change and global warming and all of that. But there's more to this. When we drive and when we sit in traffic congestion, idling our engines, there is like a series of pollutants that we are emitting, anything from carbon monoxide, nitrogen oxide, sulfur dioxide, and so on. And this is alarming. Based on research stats, about 60,000 premature deaths annually is happening due to lung cancer, asthmas, respiratory infections, and things that are direct impacts of these types of pollutants. So whether you want to look at it from a sustainability perspective in terms of environment, climate change, or health perspective, this is a big issue that we need to focus on, and we have. And again, by we, I mean the transportation sector. So what have we been doing?
That number is like national or any?
This is for the US, national. So what have we been doing in the transportation sector? At least over the last 2 decades, transportation engineers, planners, transportation authorities, policymakers, planners, just about everyone has been sort of like working on fuel strategies, vehicle strategies, travel demand management strategies, land use strategies. We refer to this picture as a 4-legged stool. And we believe as transportation professionals that all of these strategies, whether it's a fuel strategy or vehicle strategy, they all need to come together in order for us to achieve sustainable transportation, a sustainable transportation system. One on its own is not going to do, it's not going to be enough. I have a few examples of each fuel strategies. We've heard about ethanol and compressed natural gases, hybrid vehicles, plug-in hybrids, electric vehicles under vehicle strategies. Travel demand management strategies could be anything from encouraging people to bike, teleworking, basically incentivizing people to work from home, improving our public transit system. Anything that lowers or would lower vehicle miles traveled would go under this category. And last but not the least, we have land use strategies, things like developing brownfield sites or mixed-use developments where people could live somewhere that is close to shopping centers, daycares, and that would reduce their vehicle miles traveled. So this is sort of like a mishmash of different strategies that planners and engineers have been working on in order to achieve sustainable transportation systems. And then something happened about a decade ago. the idea of driverless vehicles, autonomous vehicles, self-driving vehicles, and everyone kind of slowed down. Everyone in the industry is like, okay, this is our silver bullet. It's going to solve every single problem that we have. There was a hype that started with Google about a decade ago on their self-driving vehicles, and following that, lots of news. And I'm sure every one of you have heard about this or read about this, that how self-driving vehicles are going to come to rescue, and they're going to basically make our life much better. They are going to bring us safety, no more accidents when they come, and that we can use them on our public roads. We're not going to have traffic congestion on our roads. As a result of that, we're going to save a lot of time, and of course, consequentially, we're going to reduce our CO2s and environmental impacts. And as a result of this, we're going to have a happier life. And I'm here today, unfortunately, to tell you that is not the truth. That is not what's going to happen. So my research basically involves looking carefully at the impacts of this new disruptive technology and see how much of what we've been hearing in the media over the last decade has been a hype or reality, or what's going on and what we are expecting. Okay? So on that note, I'm going to give you a quick overview, historical overview of vehicle automation. I'm going to define levels of automation, and then I'll give you a scope for this particular study, the method, and some results on energy savings and environmental cost-saving results.
How long?
I think even if we don't watch this, I've already gotten my point across. We're not ready. We're not ready for this technology, okay?
People have been trying to make cars drive themselves. Well, almost as long as there have been cars. This article about a remote-controlled car is from 1925, but it's in the 50s that the race to develop a truly autonomous vehicle really gets going. In 1956, GM unveils a futuristic concept car called the Firebird 2, but it's not the Firebird you know. It looks kind of like a fighter jet, and it's controlled by a magnetic strip embedded in the road. GM envisions a driverless future so wonderful, families literally sing about it. In 1958, GM teams up with RCA to develop a driverless car that uses radio frequencies to navigate. It actually works, and the cars are supposed to be commercialized by 1975, but that, of course, doesn't happen. Fast forward to 1986. Carnegie Mellon develops a driverless Chevy van called the NavLab 1. It's packed full of computers and doesn't work so well. But GM sees potential and later teams up with the university to explore driverless technology. In 1998, Google is founded. In 2004, Google goes public. More on them in a second. In 2005, the DARPA Grand Challenge is held to award $2 million to a team that makes a driverless car. A car named Stanley, developed by a guy named Sebastian Thrun, wins. Thrun later goes on to found Google's secretive tech research program, Google X. At the 2007 DARPA Challenge, Thrun and his team placed second to the GM Carnegie Mellon team in their Chevy Tahoe Boss. In 2008, the financial crisis hits. GM cuts jobs. It teams up with Segway and unveils an autonomous concept vehicle built with the same technology used in its 2007 DARPA-winning car. Google, flush with cash just 5 years after going public, expands its driverless car program, and the race between Google and GM kicks into high gear. Metaphors. In 2011, GM and Segway make the NV, a refined version of their earlier model. In 2012, Google unveils a fleet of test vehicles retrofitted with a driverless rig. States start passing laws allowing driverless cars. 23 Google cars drive themselves on the roads of California and Texas. In 2014, Google expands into GM's territory and builds its own car, without a steering wheel or pedals. It looks like a cute little toy, but people seem to like it. In 2015, GM shows off a Cadillac with a Super Cruise feature that drives itself in highway traffic. They plan to start selling the flagship CT6 sedan to the public in 2017. Maybe. Meanwhile, Google says they've already driven over 1 million miles in their driverless cars. But the vehicles haven't been tested in heavy rain or snow, and they sometimes can't distinguish between trash and people. Despite that, we could see Google's car available to the masses as early as 2017. It's a tight race, but we're likely to see the winner sooner than we think.
So what I wanted to draw your attention to is that, first of all, this technology called autonomous vehicles or driverless vehicles is nothing new. We have been hearing about this since 1920s by GM's, when GM made the exhibition of their visionary driverless car not too far from here in Flushing, New York. And this was sort of like their idea of how it would look like. This was actually working driverlessly. And then, as we heard, there were like series of DARPA challenges in 2000s, 2007, 2008. Stanford was a big player. Carnegie Mellon was another big player. And then it came Google a little bit later, and that kind of like helped public to get themselves familiarized with the technology. And this is sort of like more or less where we are now. I can also tell you a little bit from my own experience back in 2013, 14. I was still with Carnegie Mellon. I was working with the Pennsylvania Department of Transportation doing an impact analysis project. The state of Pennsylvania wanted to know what would happen to anything and everything that they own and operate when this technology gets materialized. And we were working on that project with them. It was a one-year research project, very high level. And because of that project, or as part of that project, I used to go to DC and make a few presentations to our congressional delegates. And back then, in 2012, 2013, only 6-7 years ago, I remember a few congressmen sitting in front of me telling me, no, I don't believe in this. That is not going to happen. It's for younger people. You guys do it. You guys try it, but not for me. And these pictures were taken actually, or exactly a year after those talks, where you can see here that they are all very excited. There was a lot of news and media attention that this technology was getting. Every senator and congressman and everyone in DC wanted to do a test drive and put their name out there as supporters of the technology and so on. But the hype is kind of over again. Like we've seen like the hype in 1920s and then 50s and then again 70s. And 2000s, and now it's kind of like, we're over the hump. And now we are sort of like in a phase where things are a bit more realistic. People know what's going to happen and what is not going to happen. Okay, there was a lot of confusion on terminologies when it comes to driverless and automated vehicles. What does driverless mean? Is driverless vehicle the same as autonomous vehicle? So same as self-driving vehicle, which is a terminology that was invented by Google. A lot of confusion around that, even within the professionals who are working in the field. And finally, a few years ago, 3-4 years ago, the Society of American Engineers and NHTSA, they came up with some guidelines to help everyone understand, or having the same terminologies. And one thing that they did was that they put different levels of automation into different categories. So right now, everyone who is working in this industry knows that we have what's known as 5 levels of automation. It starts with level 0. Level 0 obviously is no automation, but sometimes it gets confused with level 1. The reason is that any warning system that you have on your vehicle, like right now a lot of vehicles have lane keeping warnings, like if you want to change lane, something starts beeping, or blind spot warning. Those warning systems are not any part of automation. Those are still level 0. And then we have level 1, where the vehicle can assist the driver or take control of either the vehicle's speed through cruise control or its lane position through lane guidance, like very limited. In terms of assist package and what the vehicle can do. Level 2 is occasional self-driving, where occasionally your vehicle can take control of both vehicle speed and lane positioning. So you have a car that can keep itself in between two lanes and goes like with a certain speed and keeps its distance with the car ahead of it. And that is where we are right now. That is level 2 automation, and that's what Tesla has done. So any vehicle that we have today on our roads under driverless, automated, I really don't care what the terminology is basically at level 2 and nothing beyond this.
Level 2 does the parking also?
Level 2 does not do parking. I'll talk about that in a little bit. So anything on public roads that cars are doing in terms of automation is basically level 2. Beyond level 2, we don't have anything on our public roads. Okay? I want you all to be clear about this. Level 3 is where the car can drive itself in some situations, but the driver would still need to sit there in case the driver would need to take over the control. So like for a limited period of time, the car can drive itself, but it might come to a point that it would need driver's help. So the driver still would need to sit there. From the regulatory perspective, policy perspective, permissions, no automotive company has yet the permission to put a level 3 car on our public roads in the United States of America. Level 4 is when we have a self-driving car in an isolated zone, whether that's a test zone or a parking lot. So Tesla's parking, new parking, automated parking assist, what is it called? Smart. Thank you. That is level 4, but it's only on private roads, private lots. Parking lots are considered to be private. Again, not on public roads. Local areas. Test areas, test beds. We have a number of test beds across the country. Only those. Level 5 is what we know or we think of when we think about the future of this technology, when we say driverless. Level 5 is when the car can drive on its own, by itself. It can do anything and everything that you and I can do in every single situation. So I'm going to repeat this. The car can do anything and everything that you and I can do, and I want you to think about this.
I have a question.
In every single situation, please.
Why is that so preposterous? If given deep learning and where artificial intelligence is taking us.
So that's sort of like outside of the realm, outside of the scope of this talk, but I'll just give you a couple tips on that. From the regulatory policy perspective, we're not there. The government is not basically allowing us to go there. From the the technology more or less is there. We're not confident yet. Right. You can see like every testing, everything that you see, every car, like whether it's Waymo or Tesla or Uber or whoever is doing driverless cars testing, it's either in California, Arizona, Florida, or a state like that. It's never in Michigan or New York, or because weather is a problem. So we're still not sure from the technological perspective if we are there. But I'll give you a couple more examples that might sound more interesting to you. If you and I are driving and we see a pedestrian standing by the curbside, just by looking at that pedestrian for a second, we know or we can guess pretty accurately what the intent of that pedestrian is. If he is intending to cross, or if he's just standing there reading a text, or if he's waiting for a bus. For an algorithm to have that level of cognition, we're still not there, okay? So what happens as a result of that? When the algorithm is not there, when the machine is not there, what happens, it could result in a lot of false positives. So you don't want the car going driverless stop every second because he doesn't know if the pedestrian is walking across the street, or if this is trash, or it's not human, or whatever scenario it is. We're not there yet. From the ethical perspective, for the vehicle to decide, for the AI algorithms to decide in extreme cases, if they would go, if they have a truck going ahead of them, if it's better for them to hit the truck, or it's better for them to go curbside and hit a bunch of pedestrians that are walking on the sidewalk. So kind of like the old trolley problem, for those of you who are familiar with that. So there are a lot of ethical concerns with that as well. I can go on and on in terms of what the problems are, but let me stop here and just tell you that, again, everything that we have on our public roads is level 2. Level 3, because of liability issues that comes with it, it's kind of like some companies are saying we don't want to even do level 3. We're going to skip level 3 and go to level 4. Some companies are saying no, we will do it. It gives us some good idea as how to fine-tune the technology. Level 4 is in isolated areas, so you'll see them in parking lots. You'll see them in some airports, isolated areas. Level 5 is far, far, far away. It might happen, maybe may not, I don't know. But the closest predictions, the most realistic predictions right now are 2070, 2100, if then.
Do you think for it to be level 5 that every car on the road would need to be level 5?
No, and my personal judgment is that it will never be like that. So we will at some point probably have driverless vehicles, like level 5 vehicles, but more for hailing services, ride sharing, trucking industry, deliveries, things like that. But for us to have like that utopia world where everyone is driverless, I don't see that happening.
We have several presidential candidates who are talking about vehicle autonomy.
Mm-hmm.
And taking jobs from the trucking industry. So maybe level 5 is not there just yet for just us, people who are just driving every day to go to the shopping, to go to get groceries, so on and so forth. But is it there yet for trucking or for ride sharing?
I can tell you that trucking industry is the #1 industry that's making advances and actually putting this technology into use. So we will see this probably sooner than later with the trucking industry. Now, to what capacity, how they're going to limit it, what kind of boundaries they're going to put around it. Are they going to have drivers sitting behind that wheel? Probably yes. For how long? We don't know, but that's sort of like the direction we're going. In terms of economic forces and what's going to happen with jobs and stuff in the trucking industry, I think that it's just the nature of our world. Jobs, people, we are way we have gone far away from days that we used to take our parents' profession to the point that we kind of came to conclusion that we can do our own things. We don't have to follow what our dads or moms were doing. And now we are actually gradually moving out of this phase. And I think we ought to sort of train ourselves to be able to dynamically shift our jobs, go from one job to another. I think within the few decades, this whole idea of I study one thing and I'll do that one thing for the rest of my life is going to be history. It's not going to work like that. So we need to sort of like be able to adapt to this fast-paced life and changing environment. But let me continue because we're getting away from the actual topic of this study. So as I said, in this study, we focused on driverless or vehicle automation and their impacts on energy and environmental sectors. One other thing I should mention before I move forward. In 2013-14, we wanted to do this study. This is back when I was in Carnegie Mellon still. We wanted to do this study, the impacts of automation on energy, fuel consumption, and environmental issues. And soon we realized we certainly cannot do it for level 3, 4, 5, because we don't have data. And even for level 2, it was sort of like difficult. So we stopped. We stopped very quickly. It was a project that Toyota wanted us to take on. We did a high-level analysis for them, but we really didn't go into depth with that. Fast forward to 2016. I decided to take on that project again with one of my PhD students here. And this time, I was wiser. I knew that I cannot have data on level 3, 4, and 5 because there is no car out there on level 3, 4, and 5. So any analysis we do on those levels, it's not going to be really relevant. It's going to be based on a lot of assumptions. And there is a point where you're making so many assumptions that kind of brings the validity of your study under question. So we decided not to take that route. Instead, focus only on what we have right now and what is plausible, which is level 2. So this study and the scope of this study is basically around level 2 automation. Level 2 automation includes many technologies. We decided to focus on 12 of them. We have anything from lane departure warning, active braking, lane keeping, adaptive cruise control, cooperative adaptive cruise control, blind spot warnings, collision detection braking, dynamic route guidance, traffic warning, forward collision warning, and so on. Some of these are warning systems. They're not even automation. They're level 0. Some of them are level 1. Some of them are level 2. But this is sort of like, these are the 12 technologies that we focused on to see what's the impact of these technologies on fuel consumption and environmental damages. How did we go about this? We started looking at impacts of these technologies on accidents and congestion that's resulted from accidents. We also looked at impacts of these technologies on non-accident related congestion. Like sometimes accidents, sometimes congestion, traffic congestion is because of accidents, sometimes not. We wanted to sort of examine both of them. We wanted to see how these technologies would impact drag forces and aerodynamic forces between two vehicles. So we looked into that. We also wanted to look into operational loads. We well knew that each of these technologies would include a lot of sensors and like operational load within the vehicle, and that consumes fuel by itself. And we wanted to take that into effect and to take into account. And also traffic rebound. Traffic rebound meaning that if we are saving some energy on one aspect, how are we going to use that elsewhere? If we are saving vehicle miles travel, reducing congestion, is that going to induce more traffic on our roads? So this was really a holistic study that we did in terms of positives and negatives that would come with these technologies, not just benefits. In terms of pollutants, we looked at a variety of them: CO2, CO, NOx, particulate matters, NH3, VOC. You'll see the list. So these are basically the pollutants that we focused on. In terms of methods, we basically brought a few models together and made this massive model that gave us what we wanted: automated technologies, impacts on fuel consumption, and marginal cost of emissions. And we focused on 86 metropolitan areas across the United States. We wanted to know not only what's the impact of the technologies on fuel consumption, but we also were interested to know if the impact would be different from one area to another. If the impact of one technology would be different in New York compared to Los Angeles area, compared to Detroit, Michigan. So we looked at light-duty vehicles emissions and energy consumptions based on speed. We looked at capabilities of each technologies in terms of reduction in accidents, reduction in non-accident related congestions, drag forces, and so on. And we coupled these with marginal unit costs of air pollutants per county. We used the APEEP model. APEEP stands for Air Pollution Emissions Estimation and Policy. It's an integrated assessment model that basically looks into how basically links emissions with exposure level and physical effects and monetary damages of each pollutant in each county across the United States. So it's a very comprehensive model. We merge these data with metropolitan-specific travel data in terms of speed, the amount of congestion, rush hours, how many hours people are sitting in congestion and whatnot, and of course US Census data, and we got some interesting results. So this first chart that I'm showing you, this is on fuel savings with 50% market penetration rate. Just a quick note on market penetration rates. This study, and I do have the manuscript here, and I can share it with you if you're interested. We basically looked into, this was very much a disaggregated study, so different market penetration rates. What I'm going to show you here, it's either 50% market penetration rate for each technology or 100%. But we also looked into 10%, 20%, where we are right now, and so on. But just to give you an idea, fuel savings with 50% market penetration rate. On the y-axis here, I have percent energy saving potentials. On the x-axis, you will see each of those 12 technologies. Okay? And the coloring is associated with each of those impacts, like the non-accident related congestion reduction, the accident related congestion reduction, operational load, traffic rebounds, and so on. Interestingly, when you are looking at warning systems like lane departure warning, collision warning, blind spot warning, speed limit detection, traffic warning, we do not see any benefits in terms of gas saving. None. It's all negative. It's all operational load, basically, because we're still consuming those loads, right? When it comes to adaptive cruise control and cooperative adaptive cruise control, we see some impacts, and again negative. And then when it comes to parking aid system and dynamic route guidance, we see some positive impacts. So the 4 technologies that we quickly figured it has the most amount of impact on energy consumption and consequentially environmental impacts were adaptive cruise control, cooperative adaptive cruise control, and parking routing systems, as well as dynamic route guidance and parking aid system. Parking aid system and dynamic route guidance give us the most of the impact because of non-accident related congestion detection. Because a lot of people, especially in metropolitan areas, go around CBDs, central business districts. They're just driving because they're looking for parking. And that adds quite a bit to vehicle miles traveled and the consequential fuel consumption. So if we use parking aid systems...
When you say cruise control, using cruise control give less gas consumption in there?
Yes, so I'll get to that. So with parking aid systems and dynamic route guidance, I just want to make the differentiation here that you see the blue columns more than anything else, and that is because of non-accident related congestion, because route guidance also, just like parkings, would navigate you to go to less congested areas, and it will reduce your VMT. When it comes to adaptive cruise control and cooperative adaptive cruise control, what's happening essentially is that you are reducing the drag forces between 2 cars. And just by reducing the aerodynamic forces, you're reducing gas consumption. And that is where we see the biggest impact here. And of course, some non-accident related congestion, but that is not coming from the adaptive cruise control part of this. That is coming from the cooperative part of it.
What is aerodynamic force reduction?
There are different, so based on the headway between the 2 cars, you have a certain aerodynamic forces. I don't have the equations and formulas that we put into.
One car is tailing right behind the other?
Yes.
Drag force?
Yes, yes. So it's all about the headway velocity and the distance between the 2 cars. But any more details than that, I can talk to you offline if you're interested in the physics part of it.
No, I just was wondering.
Yes, yes. So, okay, so this is sort of like where we, okay, and again, you know, we've done this for different market penetration rates, and the general idea was that it's pretty intuitive. As market penetration increases, the savings would increase. Just like any good researcher would do, we wanted to compare our results with other studies that are out there. We're lucky in this case because the number of studies that are out there are not that many. But here is like a handful of them. And what you'll see here, and what led to success of this particular paper, it's already published, it got the best paper award or best presentation or whatever, is that we could successfully reduce the uncertainty. If you compare the results, we're saying $60 to 266 savings or dollar savings per year per vehicle. You see some of these other studies are going from minus $2,063 to $1,132, minus $975 to $542. So the range was huge, a lot of uncertainty in their analyses. We could kind of narrow that down, and our results were a lot more realistic. Low-level automation, these are our takeaway points from this part of the research. Low-level automated vehicle owners could save 6 to 23% fuel, equal to 60 to 270 US dollars per year. And all road users could save up to 10 gallons per year. By all road users, we mean those who do have cars that are equipped with these technologies and those who don't. Because if you reduce congestion, you're impacting essentially everybody. Adaptive cruise control, cooperative adaptive cruise control, dynamic route guidance, and parking aid systems have the highest fuel saving capability. The next part of this research was, again, to use the APEEP model and to link the data that we had on fuel consumptions with APEEP so that we know what's the social cost of or cost savings of these technologies. And what we did was that in terms of social cost, we wanted to do what's the monetary value of mortality, morbidity, and environmental damages today and with these technologies. So again, a very detailed studies for 86 metropolitan areas, different penetration rates for all these pollutants that I've listed at the beginning of the study. And it was interesting. For mortality and morbidity, we had to assume value of life. And value of life, those of you who worked with this, is a very tricky subject. Economists estimate value of life generally at about $120,000 per life. EPA goes as high as $10 or $11 million per life. So there is a wide range for value of life. I'm sure if I ask each one of you how much you think your life is worth, it would be a very difficult question to answer. We used EPA's number. We used $11 million per life. But again, you know, linking this back to what I was telling you at the beginning, a lot of premature death is happening as a result of driving and congestion when it comes to like lung diseases, respiratory infections, and so on. So this is important: mortality, morbidity, and environmental damages. The same pattern we're seeing here: cooperative adaptive cruise control, parking guides, and dynamic route guidance is what we're seeing that has most of the impact. We could not use APEEP for CO and CO2, so we had to use different cost levels for those. But again, the same pattern continues for 50% market penetration rates. Low-level automated technologies, total emissions cost savings by impact categories and penetration rates. So these are the various impacts that you see here. On the y-axis, I have social cost savings, million USD per day versus market penetration rate. And you can see how the trend is going to look like. But I want to get to this, and I know I'm short in time. I've already been given the 5-minute signal. This is sort of like my favorite sort of takeaway slide of this. What this is showing you is that how different, how social costs or social cost savings of each of these technologies would be different across the United States. So the colors noted here are emission cost savings per vehicle miles traveled. This is all in 2019 dollar amount. And the size of the circles are emission savings per day, again, 2019 dollars. And as you see in and around the Los Angeles area, New York area, we have sort of like the larger circles where it would mean that emission savings are larger per day. And then in terms of color, like down here in San Diego area, I see this hot red. And what that tells us is that each of these technologies could have a different impact and certainly different social costs in different areas. And I'll just give you, so this shows you 4 of these technologies, the 4 that had most of the impacts, and the colors here associated with top 10 metropolitan areas in terms of impact. So on the list we have Los Angeles, New York, Washington, Chicago, and so on. But just entertain this with me for a few seconds. Adaptive cruise control. Adaptive cruise control could help you quite a bit in Atlanta, but it cannot help you much in Los Angeles, where 405 and 101 is constantly congested. More cars on the street. By the same token, parking aid systems could be very useful in downtown Los Angeles area, but perhaps not as useful in other areas. So this is sort of like what we wanted to show, that each of these technologies could potentially have a different impact in different cities. And we think that's important. And a lot of this is because of the nature of the city, the travel patterns in the city, the exposures, the geography of the city, the altitude of the city, you know, how pollutions and exposure, how people are exposed to pollution, the density of the city, and so on. So I have 1.5 more slides. So these are takeaway points from the environmental part of the study. Low-level automated vehicle technology have the potential to reduce emissions, marginal damage up to $12 billion annually. That would be equivalent of 2,000 lives. These technologies could decrease emissions by about 25% in 86 metropolitan areas. And the amount of emissions are dependent on level of congestion, marginal unit cost, and so on, percent highway travel. Now, what does this mean? So what? Like in terms of policy, what we wanted to get out was that really like agencies, policymakers could do a better job in terms of incentivizing the right technology in their areas, promoting them, prioritizing them, and do more of a targeted adoption for each of these technologies. I also wanted to say that this work could have not been finished without Saeed Wasabi's help, who is my PhD student sitting in the back here. And if you have questions, we are happy to answer them.